in our previous class we've discussed different types of methods, right? The first one is what? Double integration method, Macaulay's method, moment area method, and a lot of methods, right? Now we want to look at moment distribution method. We want to look at what? Moment distribution method. Here's what you should take notes. Basically we have different types of beam, right? Basically we have different types of beam. The first one is what? Statically determinate beam, and the second one is what? Statically indeterminate beam. From here we said that we want to look at moment distribution method, right? Now what's the idea behind moment distribution method? Basically what we know is that we have two different types of beam, right? The first one is what? Statically determinate beam. The other one is what? Statically indeterminate beam. Are you with me? Now when we did our introductory video, we've seen different types of statically determinate beam and statically indeterminate beam, right? The one we know is statically determinate beam, meaning our single supported beam, overhanging beam, and cantilever beam. Now under this guy, statically indeterminate beam, they are just two. They are just what? Two. The first one is what? Fixed beam. The first one is fixed beam, and the second one is continuous beam. Given a statically determinate beam, say simply supported beam or cantilever beam, we can draw the shear force and bending moment diagram, right? We can draw the shear force and bending moment diagram. Now let's say you are given a fixed beam or you are given a continuous beam. How do we draw this shear force and bending moment diagram? How do you draw this shear force and bending moment diagram? That's what we want to do. And we said we have a lot of methods. We said we have a lot of methods. There are a lot of methods, right? Out of this method is called moment distribution method. Meaning we have a lot of methods to analyze statically indeterminate beam. Out of this method is called moment distribution method. We also have Clapeyron's three moment equation. That one is different from this. You are making your bending moment diagram. In this case, you are using formulas and you are drawing your table. Now let's see how it works. Before we proceed, I'm going to use this fixed beam to explain. Because now, say you are giving this fixed beam. Say this is A, this is what? B. I guess what I'm saying. Say this is A, this is B. The question says that draw the shear force and bending moment diagram of this fixed beam. Draw the shear force and bending moment diagram of this beam. You are going to draw two bending moments. You are going to what? Draw two bending moments. The first one is due to the support, meaning the fixed support, while the second one is due to what? The vertical loading. The first one is what? Due to the support, due to the fixed support, which is the support at A and the support at what? B. While the second bending moment is due to what? The vertical loading. Meaning you have two bending moments, then your final bending moment diagram becomes the addition of the two. Now let's say you have this fixed beam. Let's say you have this fixed beam loaded with a UDL and a point load. Call this A, call this B, call this C, call this D. Drawing my free body diagram for this beam, it becomes this, right? I have this. I have a moment at this point. This is B, this is A, call this RA, call this RB, call this moment about point A, and call this moment about point B. Now, drawing the bending moment diagram for this beam, my first bending moment diagram is due to this vertical loading. Is due to what? This vertical loading. From this, say this is case 1. From case 1, you can bring out two diagrams. This is the first one. This is the first diagram. And the second one, this is the second one. This is A, this is B, and this is what? This is still A, this is what? B. This is moment at A, this is what? Moment at B. You know, initially, given this question, this is my free body diagram, right? Let's say we've calculated the value, the unknown value. I've already calculated it. Now, I want to answer the question itself, which is what? Draw bending moment diagram. You agree with me that from case 1, I have 2 diagrams, I have 2 structures. This is my first one, this is my second one. You know, you can relate this to the usual one that we know, which is what? Simply supported beam. I get what I'm saying? Meaning, for this simply supported beam, I'm going to draw my bending moment diagram. And for this moment at each end, I'm going to draw my what? Bending moment diagram. So you are going to bring this bending moment diagram and this bending moment diagram. You are going to bring it together. And this will now give you the bending moment diagram due to this fixed support, due to this fixed beam. Now, in general, what it means is that giving a fixed beam, in general, what it means is that giving a fixed beam, you want to draw the bending moment diagram of that fixed beam. Your first task is to what? Draw the bending moment diagram due to what? The fixed support. Right? The second one is what? Draw the bending moment diagram due to what? Vertical loading. Due to vertical loading. This is another aspect on its own. But we are just implementing the same idea here. So that's why I brushed through this. Now, back to this question, moment distribution method. When it comes to moment distribution method, it is quite easier in the sense that we just need to know the formula that we want to compute this value. We just need to know the formula that I want to compute the value. Now, first thing first, given this beam, you are going to assume that each beam is fixed. You know, from this beam, we want to start our solving now. Solution. Now, you are going to identify at point B, what type of support do you have there? You have a pin support, right? This support is called intermediate support. You have point B, right? You know, from here, you are interested in knowing the value of moment at each support. You are interested in knowing the value of moment at A, of moment at B, and of moment at what? C. Now, how it works is that from here, given this type of beam, say you have a simply supported beam, or you have a cantilever beam, you are going to do an assumption that call this A, call this B, call this A, call this B. This is call this 1 and call this 2. For the first one, identify at point A and at point B, what type of support do I have there? I have a pin support. But as far as this method is concerned, you assume that this pin support, they are fixed. They are what? Fixed. So in general, you are going to assume the support of your beam as what? A fixed support. Now, let's say you have this initially from the question, this is what I have. But now, my assumption is that this one is still the same thing as what? This. Are you getting my point? Similarly, for 2, you know, this is a cantilever beam, right? At point B, it is a free end. But your assumption, as far as moment distribution method is concerned, it becomes what? This guy. Are you getting what I'm saying? So now what we are saying is that given a beam, you are going to assume that the support of this beam is what? Fixed. It is a fixed support. You are going to separate your beam. When I'll be using the word span here. When I say span, I mean what? Length. When I say span, I mean what? Length. Now, this given beam, you have what? A, B, C. You can separate this beam as what? Span AB and what? Span BC. True or false? True. You can separate it as what? Span AB and what? Span BC. Meaning, for span AB, I have this guy. Span, this is A and this is B, right? I have a UDL. The length is what? 4 meter. What's the intensity of this UDL? 10 kilonewton per meter, right? Now, for span BC, For span BC, same idea. Bring out your beam. We have this. This is 15 kilonewton. This is 3 meter. This is 3 meter. This is B, and this is what? C. Given a question, your first task is what? You should make what? An assumption. And what is this assumption? You assume that the support of this beam is what? Fixed. The support of this beam is what? Fixed. Meaning, for span BC, this is what you have there initially. Based on your assumption, you can withdraw this as what? This, right? This is 3 meter. This is 3 meter. This is 15 kilonewton. This is B. This is C. Similarly, for span AB, you have your new beam as this. This is A. This is B. This is a UDL, which is what? 10 kilonewton per meter. And this is a 4 meter. This is your first task. This is your first task. Now, the idea behind this is that for every fixed beam loaded with different types of load, you have formula for the fixed end moment. Any fixed beam of this nature having a center concentrated point load P kilonewton of distance. This is A, this is B, this is C. The total length is L meter. From here to this place is L over 2. This is L over 2. Tell me the fixed end moment of this beam. Fixed end moment at point A minus PL over 8. Tell me the fixed end moment at point B. Positive PL over 8. So that same PDF, check. Beam of this nature. Tell me the fixed end moment. This is A, this is B. Tell me the fixed end moment of A. What's the formula? Minus WL square over 12. The fixed end moment at point B is what? Positive WL square over 12. You observe that the sign, it is just the sign that is different. At point A, you have negative. At point B, you have what? Positive. Right? Now, from here, call this one, call this 2. For the first one, 1 and 2, respectively, what span am I relating it to? For 1, for figure 1, or you say for case 1, am I relating it to span AB or span BC? Span AB. For case 2, AB or BC? BC. Now, what it means is that up to this level, you are going to calculate the fixed end moment at B, the fixed end moment at C for what? Span BC. Similarly, you calculate the fixed end moment at A and the fixed end moment at B due to what? Span AB. Due to what? Span AB. Also take note that for this type of fixed beam, the moment due to vertical loading, is given as WL square over 8. WL square over 8. The beam of this nature, any fixed beam of this nature, the vertical moment is given as PL over 4. PL over 4. Now, from here, for span AB, let's get the fixed end moment. Fixed end moment at point A. That will be what? Implementing that formula, is it case 1 or case 2? Case 1. Meaning negative, identify. What is your W here? Let's do this together, please. What's your W? Meaning 10 times what's your length? 4 square divided by 12. This is the fixed end moment due to what? Point A. Now, fixed end moment due to point B. What's the difference? The sign, meaning positive 10 times 4 square over 12. Now input this in your calculator. What's the answer? -13.33 kilonewton meter. For fixed end moment at B, what's the answer? Positive 13.33 kilonewton meter. Now let's calculate the moment due to vertical loading. Moment due to the vertical loading. What's the formula? What's the formula? WL square over 8. WL square over 8. Now, what's your W here? Identify. What's your W? 10. Meaning 10 times 4 square all divided by 8. What's the answer? 20 kilonewton meter, right? Now, fixed end moment due to point B, -15 times 6 over 8. Due to point C, at point C, that's what? Fixed end moment at point C. Just positive 15 times 6 over 8. What's the answer to this? Negative 11.25 kilonewton meter, right? Then this one is what? Positive 11.25 kilonewton meter. Now let's calculate the moment due to vertical loading. Moment due to the vertical loading. What is the formula? WAB over L. Now identify. What is your A? What is your B? This is your A and this is your B. Meaning I have 15 times 3 times 3, all divided by what? The length, which is 6. To positive 22.5 kilonewton meter. Alright, now let's be fast with what's that? WAB. WAB. This is A, this is B. Now, from here, let's quickly recap before we proceed. We said we separated the span, right? When we separated the span, for each span, we calculated the fixed end moment and the moment due to the vertical loading of each span. Now, next step, calculate stiffness factor. Calculate stiffness factor. Now, take note, when it comes to stiffness factor, hello, are we together? Now, the next step is what? Calculate stiffness factor. When it comes to stiffness factor, here's how it works. If your beam is having a fixed support, the stiffness factor becomes 4EI divided by L. 4EI over L. If your beam is having a fixed support, the stiffness factor becomes what? 4EI over L. If your beam is having a pin support, roller support, or a hinge support, the stiffness factor is what? 3EI over L. 3EI over L. Now, calculate stiffness factor. When calculating stiffness factor, if the type of the support your beam is having, if it is pin, roller, or hinge support, your stiffness factor, take note, your stiffness factor is represented as K. Meaning, for this type of support, your stiffness factor K is equals to 3EI over L. If it is fixed support, for fixed support, your stiffness factor K is equals to 4EI over L. Now, meaning for span AB, I'm going to get stiffness factor. And for span BC, I'm going to get stiffness factor. Now, this is how you go about your stiffness factor. Your beam, the given beam, go back to the middle. Now, from this place, you have span BC and span BA. You have span BC and span BA. Now, say you're on point B. Let's have the stiffness factor of span AB first. Now, say you're on point B to A. On getting to A, what type of support do you have? If you have a fixed support, what's the formula for your stiffness factor? 4EI over L. Meaning that for span AB, that is stiffness factor KBA becomes what? 4EI over L. Same idea. Say on this point B to C, on getting to C, what type of support do you have? Identify what type of support do you have? Pin. You have a pin support, right? You know, your pinch support, you can still categorize your pinch support as your hinge support or roller support, because by the time you draw your free body diagram, this is hinge support, this is roller support. By the time you draw your free body diagram, this is what you have for the R, this is what you have for the vertical reaction, right? For your roller support, by the time you draw the free body diagram, this is what you have for the vertical reaction. So what it means is that at any point at your beam whereby you have these two type of reaction, you can still categorize it as either pinch support or roller support. That's why they are saying that if you have pinch support, roller support or hinge support, the stiffness factor remain what? The same. Now say you're on point B to C. On getting to C, what type of support do you have? What type of support? Pinch support. What is stiffness factor for pinch support? 3EI over L, meaning that the stiffness factor of span BC is equals to what? 3EI over L. For span AB, let's calculate the stiffness factor, meaning KBA. What will be the formula? Let's do it together now. That's 4EI over what? L. 4EI over L, which implies 4EI. What is the length of your span AB? That's 4. Meaning 4 cancel out. What do you have? EI. Now moving on to the next span, which is what? Span BC. Let's calculate the the stiffness factor of span BC. What will be the formula to use? 3EI over L, which implies 3EI. Substitute. What is your L? 6. This is span BC. 3 plus 3 will give you 6. 3 go here 1, 3 go here 2. What do you have? EI over 2. Now let's get the summation of stiffness factor. Summation of stiffness factor. By summation, meaning the stiffness factor of the stiffness factor of span AB plus the stiffness factor of what? Span BC. Now substitute. What is stiffness factor for BA? That's what? EI. What is stiffness factor for span BC? EI over 2. Take LCM, meaning 2EI plus what? Plus EI, which is equals to what? 3EI over 2. Meaning this is the summation of your stiffness factor. Now let's calculate distribution factor. Distribution factor at each span. By distribution factor, this is the formula. Distribution factor D is equals to stiffness factor K divided by the summation of stiffness factor. Now let's solve the distribution factor for span AB. Identify what is your stiffness factor for span AB. EI. What is the summation of stiffness factor? 3EI, meaning EI over 1 divided by 3EI over 2. Of course, this division will change to what? Multiplication, meaning I have EI over 1 multiplied by 2 divided by 3EI. Observe, EI cancel out, meaning that the distribution factor at AB is equals to what? 2 over 3. Similarly, let's solve the distribution factor for span BC. That becomes what? Identify. What is your stiffness factor for span BC? EI over 2 divided by the summation of stiffness factor. That's what? 3EI over 2. By the time this guy changes to multiplication, it becomes multiplied by 2 over what? 3EI. 2 cancel out, EI cancel out. What do you have? 1 over 3. Now what this means is that you've calculated the stiffness factor at each span and the distribution factor at each span. You've calculated what? The stiffness factor at each span and the distribution factor at each span. Then I must say, given any type of beam, given any type of statically indeterminate beam, you know how to identify a statically indeterminate beam. There are just two: fixed beam and what? Continuous beam. Fixed beam and continuous beam. This is also a statically determinate beam, right? Why? Because it has more than two supports. it has more than what? 2 support. Now this is how it works. From step 1 up to this last step, giving any type of statically indeterminate beam, that's the process. Are you know what I'm saying? Giving any type of statically indeterminate beam. Say you are giving a fixed beam, say you are giving a continuous beam. From what we started with, which was step 1, up to this last step, nothing is changing. That becomes the what? Process. Nothing is changing. The next step now, you are going to add your table. By table, you want to get the final moment at each span, at each support. You know, given this question, we are interested in knowing the moment at point A. We are interested in knowing the moment at point B and what? At point C. Now, how do you get this moment? Drawing this particular table, we are going to get it. So, meaning that different type of beam has their own process on how to manipulate the table. Are you getting the message? Different type of beam, which is statically indeterminate beam, has their own process on how to manipulate the what? Beam. But just like what we started with up to this extent, nothing is changing. Nothing is changing. Now, let's draw the table.